Don't make sure to eat.
I did.
Good? All right. Hey, everyone. So we have here a really famous United Statesian who's basically a serial inventor. Came all the way to Europe for this great talk. He's been involved with Chef, as you know, Habitat, now System Initiative, and all much more. So please give him a large round of applause. And just for the record, he's promised me lots of demos, live demos. So kill it for Adam.
You got to make it 20 minutes into the talk before you get a fucking demo, though. Okay. Look, I'm going to talk about a new theory of automation. So yeah, let's go. It's called infrastructure as model. And we're going to talk about sort of how infrastructure as model works. I'm also going to talk about sort of the underlying implementation of infrastructure as model that we use in System Initiative, which is built on a thing called a hypergraph of functions. So what I'm going to do is sort of break that theory down for you and sort of build you back up. So we're going to start from the very bottom at the most theoretical, and then by the end, I'm going to be showing you System Initiative, and you're going to know how it works. And it'll be great. You'll be explaining it to me. It's going to be sick. And then if you have questions, you can come find me on Wednesday. But you should leave understanding enough of the theory to know how you could use System Initiative to solve your own problems. OK, what do I mean when I talk about theory? I mean it the way that Peter Nauer talks about it. I think I said his last name correctly. But he wrote a paper called Programming as Theory Building, 1985. If you haven't read it, you should. It'll change your mind about what it means to program, period. And so his paper basically says, look, here's the deal. What programming is actually about is not writing code. It's not typing in the words. It's actually about the theory you construct in your mind about how the program functions. And the more complete the theory you have, the better the theory is, and the better it reflects the real world, the more high quality the work you will produce will be, right? So whether or not the software you build is good or bad is primarily dependent not upon your ability to type, but instead upon your ability to create a cohesive theory of how the program works into the world. His definition of programming is more expansive than yours is. So usually when you think about programming again, you're thinking I'm doing the typey. And that's not what he's doing. His theory of programming also includes the outside world. So when you think about what you're doing when you're programming, he's talking about programming in the large. He's saying, you're working in a domain, you got something to do. He's making a decision about how the program affects the outside world. So when we talk about programming throughout this whole talk, just remember, I'm also talking about what it does, yeah? Not just how it works. Everybody still with me? It's cool? You didn't fill up on too much Voulevant or whatever? You're taking a nap? Okay. Let's talk about theory. So theory, in this case, comes from yet another philosopher, Gilbert Ryle. He wrote a book called The Concept of Mind. I won't go into too much details. 1949, though, so it's not exactly like a new concept. Essentially, Ryle talks about two different things. There's intelligent behavior. That's the ability to do stuff. You can talk, you can move furniture around, right? You do intelligent things. And what separates intelligent things from intellectual things is theory. It's your ability to argue and think about what it is you're doing in context of the outside world. And when we talk about programming as theory building, what we're talking about is the idea that you're building up this theory. If you've ever, how many people here live with someone else or ever have? You should raise your hands because you had parents probably. I mean, whew, that got weird. Okay. Yeah, so if you've ever done that, you've probably had an argument with whoever you lived with about where the furniture should go, right? You're like, should the couch go here? Should the chair go there? Where's the painting go? In that moment, you're using your theory of how your furniture should work, the theory of how your apartment should feel, the theory of how your house will flow, yeah? That's why you can have an intellectual argument about it, right? That's what we mean when we talk about theory. So theory in programming really requires three different things. One, you have to be able to explain how the solution relates to the outside world. So the theory has to say, here's the solution of what we're writing, here's how that's going to impact what we mean in the world. Two, you have to talk about why each part of the program is how it is. Why is the program written the way it is in order to impact the world the way I want to impact it? Three, you have to be able to respond constructively to demands for modification. And this is probably the most important thing he talks about in the paper, but really what it's about is saying, if the theory is complete, when it encounters changes in the outside world, when the outside world no longer matches our theory of the program, we can change the program and our theory to match easily. This is why when you have a team of software developers, there's always that one human who knows the theory of the program, and they're the one you go to when the bugs are bad, right? Because they know how to fix it. They know how to change both the theory and the software, and you tie that construction all the way together. Because we're here talking about infrastructure automation, we're actually talking about two different theories at the same time. Theory one is how the infrastructure supports the application, right? I'm building infrastructure, I'm building some stuff. How does that work to actually build an application that you're using in the real world? And two, how does the automation that actually builds and maintain it function, right? So we're not just building that infrastructure once, we're actually building another program whose job is to then build the thing that actually does what we want to do. And we need a theory about both. So when I talk about model, infrastructure as model, for example, I'm not talking just about a data model, right? How many people here have done MVC? You've done MVC, of course you have, right? Because you're my people, because that's why I come to Belgium every year. Not that I wouldn't, Belgium's cool. But honestly, best conference. Okay, so when we talk about models, what we're really talking about is high fidelity models of real world things, right? I'm talking about it in the context of like, you have a thing in the world, a chair. How do we build a high fidelity model of a chair, right? What's that mean? And you can think about it in terms of what are the properties of a thing? What actions does that thing do, right? What can I do with it? What can it do in the world? What relationships does it have to other things, right? And then what, fundamentally, like what are the behaviors that are represented in that particular thing? Models reflect their domain. So when we talk about the outside world, domain is this idea that basically is like, I can think about the world in terms of domains of work, domains of knowledge, all kinds of stuff like that. But think about saying, I build a model of a domain. And what we mean by that is, the domain of furniture, right? And how my house will feel. The domain of automation, the domain of infrastructure, the domain of, databases or whatever, right? Okay. Let's do an example of modeling in a domain. That's a Formula One car. How many people here watch Formula One? Yay, Europe. Okay, so thing about Formula One is that the cars don't get to run very often, right? Like actually they show up at the track, they run maybe a couple hours tops before the race. If you roll a Formula One car up to the track and you haven't ever raced there before, you will lose. And when you lose millions of dollars of prize money, and it's a huge bummer. And so what they do is they build incredibly detailed, high-fidelity models of a race car, of the track, of the tires, of the body weight of the driver, of their height, like aero, wind, humidity, the track itself, like every possible variable you can imagine. They go into these very, very complex, very expensive, very proprietary simulators. And they use that to run thousands of virtual laps in every possible condition before anything even happens. That way, when they get to the track, they can extract the data from the simulator and use it to set up the car, right? That's how they have a theory of what a Formula One race car does. They have a theory of the track. They have a theory of how those things work. They build a model of it, and they simulate it. Another thing that we use that does this a lot is Unity. This is Unity. Unity models video games, right? It has a theory of what it means to do the work of video games. It understands how to do programming. It understands how to do 3D models. It can build scenes, right? It's multiplayer. It understands matchmaking, right? It does all this stuff you need in order to actually build a game Unity provides to you. When you're programming a video game in Unity, what you're really doing is programming Unity's model of a video game, yeah? Its concept of video game is the thing that you're programming, right? Okay. Our domain is technology automation, right? And when you think about it, one thing that's interesting is that we've never really modeled automation itself as a domain, yeah? We think about it as programming, we think about it as infrastructure, we think about it as all that stuff, but we don't actually think about saying, what if automation worked like video games, yeah? What if we could just model what it means to automate technology, right? That's what I'm talking about when I talk about infrastructure as model. I'm saying, let's treat it like a domain. And the properties of that domain are understandable, and we can build a model, and then we can use that model to take action. It's a hugely complex domain, right? And that's one of the reasons that we've sort of stopped short. But it turns out when you really get into it, it's kind of been the same since the 60s, right? So basically, the interface changes. You know, the API changes. Sometimes it's a UI, sometimes it's an API, sometimes it's a CLI. The way we interface gets weird, but ultimately the basics remain the same. There are properties, configuration, settings, metadata. There's actions. I do stuff with it, right? Think about a switch, top of rack switch. What do I do with it? I can plug in a port. I can enable and disable it. There's like actions I can do. There's relationships. That switch plugs into this thing. A server is plugged into that switch, right? They're the same as the API relationships that we think about modeling. And using those concepts, you can sort of rebuild a theory of how all these technology systems function, and then you can use it to your advantage. Here's an example. This is what a CloudFormation VPC looks like, just a couple of pieces, right? So if you've ever run a VPC in AWS, how many people have done that? Everybody probably? Yeah, sure, because otherwise it wouldn't work. You have properties, things like CIDR blocks, right? Or an array of tags, you know? You have actions. I can create the VPC. I can update the VPC. I could delete the VPC. You have relationships. The VPC is in a region. It has many subnets, right? And if we think about that sort of structure, you're catching what I'm metaphorically pitching. Okay, so what we're doing when we're building these models is we're building digital twins. So think of a digital twin as something that's one-to-one to the domain. You know, there's a simulation that you're making, right, that says, I have a virtual representation of some real-world thing. In our case, it might be digital. But either way, that's the component. So we think of it as like a component is the virtual side of a digital twin of something in our domain of automation. Reality is the resource side, right? So whatever the thing is that we're modeling that's real, that part we call the resource. These things are bidirectional by nature because they're both true at different moments in time or different contexts, right? So think about it this way. If you are working in the world you work in today, how many people do infrastructure as code in this room? Right, everybody, because ConfigManagement Camp. So if you think about it, except for me, I don't do it anymore because I use System Initiative and it's better. Okay, so what happens is like when you fork your repo and you're working on the definition in Terraform code, you're working on the component, right? It has no reflection whatsoever of reality. It's just you imagining what needs to change. Then later, only later, when you go to apply, does reality creep back in. How many people have experienced reality punching you in the face when you try to merge your infrastructure? Every single person, once again. Thank you so much, my people. Okay, look, it kind of sucks. When you think about it this way, though, it's bidirectional on its face. It's great if reality changes, because reality is just more data. It's just another thing that we're tracking, right? And we're also tracking the hypothetical of what you think you want to do. That would get us this idea of basically like a static model, right? So it'd be kind of easy to reason about if you were just like, well, I can build like a static data model that says the information doesn't really change, the shape of it is the same, right? But that's not the world we live in, right? We actually build horrifically complicated systems that change all the time. And so what we need are programmable models, right? If they're not fully programmable, we can't properly model the complexity that's inherent in the domain of automation. Certainly, we won't be able to model things that we haven't seen yet, yeah? Like whatever the technology is that you haven't built, we have to be able to model that thing too. So our answer to that is pretty straightforward, right? We need to be able to program the definitions, we have to program their behavior, and the whole thing has to work sort of no matter what. And so our solution to that is pretty easy. It's just functions. And in particular, we want reactive functions. So this is a little snippet of React code. This is not code that you would write in System Initiative, but it sort of shows you the idea of a reactive function. So on line 1 there, you declare a reactive reference, and you say its value is 0. That's count. Then we have a computed property called sayCount, and it just says, I am Sir Counts-a-lot, right? And then shows you the value. And then there's a function called increment-value that just adds 1, right? So then at first, when you load this, sayCount is 0. If we call increment-count, sayCount will say, I am Sir Counts-a-lot 1, because it reacts to the count changing. Now in your head, that's going to be happening because you called it twice. But that's not what actually happened. That computation would have happened immediately and then been cached and stored. So it's actually reactive immediately when the first value changed. You with me? All right, reactive functions. What we do then is we take this idea of a reactive function and we expand it to say we're actually going to build the model from a big graph of reactive functions. So think about input. A user puts in the number 2, and we have a function called double. So in the audience is Keeb. You'll hear about Keeb a little later. Keeb's favorite thing to do in System Initiative is make numbers get doubled. I don't know why, just is what it is. So it's true, he likes it. He just loves doubling. So what happens is the user puts in the number 2, we double it to 4, then we double it again to 8. Then you can imagine there's 2 other calls to double that take the 8s as inputs. They both go to 16. We have another function called sum. That spits out 32. And if you were to change any of the arguments anywhere in the chain, the recomputation would run. So if I changed the top double 8 to be double 24, right? All the things downstream would rerun. The sum would rerun. But also if I changed the first argument, all the functions would rerun. Yeah? So it's smart enough to know what's going on. It turns out that this is hugely cacheable, assuming you understand all the inputs and the functions don't have side effects. Hold on to that idea for a minute because there's definitely going to be some side effects. But you get the gist. You build a big graph of reactive functions. So if we have reactive functions, we can model properties. Properties are really straightforward. They're just value computation. Yeah? I have a function that takes some input. It produces an output. The output is whatever you want it to be. Right? So in this case, we're just going to return the VPC ID of the resource side to set this property, for example. Actions are side effects. See how quickly I got back to that? You didn't even have to remember for too long, right? Even if you ate gravy for lunch, you can still track what's happening. Okay, so it's pretty straightforward. In this case, we're just calling out to AWS. Literally, we're just calling the AWS CLI, right? So great, we can take action on whatever you want it to be. You want to call an API, you want to do whatever, go ahead, modify the world, have a party. Relationships become about argument passing and data transformation. So if I want to have a relationship between two things, what I'm actually saying is some property of that object has a relationship to some other thing. And what I'm going to do is give you 2 moments of transformation. So I'm going to say that property, again, gets output from me. And in that moment, I could transform its shape or its contents. And then I'm going to pass it to someone else as input. Then it gets a chance to transform the data. And then it gets written to some other property of itself. Could be properties, could be the order in which actions are taken, could be anything. But this idea of relationships becomes pretty easy to express in this like graph of reactive functions. Okay, that's awesome, but we also need change isolation and replay. So if you think about, okay, I have this big graph of functions, they're re-rolling all the time. How do I get back to the part where when I do work, it's unique to me, right? Which you essentially get right now at a source control. So the answer is we introduce this idea of a change set that then forks the graph, basically. So when you create it, what you're really doing is saying, I have all this data, and now I get a dimension that's sort of unique just to me, right? And that change set then tracks the changes that we're doing to this huge graph of functions. That's why we call it a hypergraph, because it's been, right, dimensionalized. It's not flat. It's actually kind of a cube, right? So we track those changes, and then we allow you to apply the changes from one change set to another, right? So you can say, you know, there's one change set that's head, you know, the world, basically, what I desire. And then you can compute yours, and then we can apply it. And when we do that, we're actually computing an operational transform. So you're just looking at this big data structure, and you're going, what's the difference between this data structure and that one? And you produce this stream of operational transforms that would transform the graph, one graph to another graph. And then we replay it to everything that's open. And the side effect is that you immediately get updated when things change. So how many people have ever been bitten by somebody else changing a resource in the real world that they didn't put into Terraform? Raise your hand. All of you. Yeah, don't lie. I see you. That can't happen in this world, yeah? Because what happens is we're tracking the outside world as a separate thing, and the transforms get computed based on the shape of it, yeah? Okay. Demo time. You with me? All right. Here's how it works. So let's start by just doing something kind of straightforward. First thing we'll do is sort of fork the universe. So we're going to say, you know, add, I got to put my note cards down. 1 second. We're going to do add VPC. All right, so that's all it took. So now we have our own little dimension, right, where everything we're doing here is isolated on our own. So we're going to go look up, see this 1,944? What that's telling you is that we have coverage of every single thing you can do in AWS. Awesome, yeah? Okay, so we're going to go get ourselves a VPC, in particular that one. Okay, so we'll drag this over here. We're going to call it like config management VPC. We'll set a cider block because you need one, you know. We'll do a /16. We'll enable some stuff. OK, what just happened when I set those values? Anyone? Raise your hand. What happened under the hood? In theory, what happened? Not you. You fucking know the answer. You work for me. Shut up. We have a new theory. Kind of, yeah. Using my theory, what happened when I did it?
So reactive function on configuration of the interface.
Yes, exactly. There was a reactive function that took what I value as input. So I wrote ConfigManagement VPC. That was the input, yeah? Which then went to a function. It was an identity function. It just means input is output. And so all it did was write it to an output position in the graph. So behind the scenes, there's a function, yeah? It's got arguments. One of those arguments in this case is user input. The user input changed. Then it wrote to the output, right? And away we go, yeah?
Is that the user input there? As a domain?
Right, yeah, these are values, right? So like when I put 10.00/16, that was user input because I wrote it in. But you don't have to write it in. Could come from anywhere, right? Just so happens that you have a web UI here, and it's nice to like type into it. I'll show you some more about that a little later, right? So we'll add a subnet now. So let's go get that bad boy. Or girl, it's honestly genderless. Okay. We'll call this like config management subnet. It needs an availability zone, so we'll just do US East 1A. That's a solid availability zone. We'll give it one of these bad boys. So it's 24. There we go. All right. So again, we did one extra thing here, which is we created a relationship, right, between the EC2 VPC and the subnet, because one belongs to the other. So in this case, now there's a value here that's called the VPC ID. You can see it down here. And it just says it's populated by a socket. Yeah? So what that means under the hood, based on the theory I told you before, what did it do?
Replace the /16 with /22.
Yeah, it understands that once that VPC gets an ID, right, that it's going to then populate it from that value. It doesn't have one yet, though, because we're working in a simulation, right? We haven't actually created anything by doing this. We've just thought about it, right? We're just working on the model. OK. Did you have a question? Did you raise your hand?
Yeah, is the cider block already checked within this model, or does that only check when you actually apply it to the
Yeah, great question. No, it's checked. Yeah, it can be checked. Not only can it be checked, you can program the checks yourself. So you could be like, thou shalt never use the 10 networks is a function you can just write in System Initiative and attach it to VPC, and now all your VPCs work that way forever. Yeah. But there's a problem, which is I can't actually apply this. Why can't I apply it? What am I missing? There's some relationships I don't have.
credential?
What's that? Credentials. That's right. I don't have a credential, and I don't have a region. You got to deploy a VPC into a region. But luckily, my friend's Keeb is here to save the day. So you might notice that it says approval over here. So what's happening is Keeb has added a credential in a region for me, which is great of him. So right now, I'm going to pop this out. We got a little view over here. See how it says account 0? So in a minute, I'm going to approve his change because Keeb doesn't have permission to actually make changes in my environment. And so all he can do is propose them, right? And so I'm set up to be an approver. So he's approved this. He's proposed this change. We're not going to go investigate, but if we wanted to, we could click on this. We could go see everything that Keeb's proposing to do. But I'm just going to approve it.
If you get further ahead, can you keep rebase?
Oh yeah, you'll see that in a minute. Not only he doesn't need to rebase because the operational transforms will do it automatically. So what's happened is now my change set, I didn't leave, right? What he's done is taken his change set, he merged it to head. So it computed a set of operational transforms. Then what did it do?
Rebase.
Shut up. People who work for me keep giving me the answers. It's the least interesting thing in the world. They. Okay, I walked into it. It's fine. But it basically rebased. But what's fun is it's not actually a rebase. How many of you have messed up a rebase? Yeah, again, all of you. You know what's fun about operational transforms when you compute them correctly? They apply no matter what, and they do nothing when the data is correct. So if I had added a credential in a region that were exactly the same as Keeb's, what happens to the graph? Doesn't change. Nothing happens to it, yeah? Because the operational transforms have already been applied from a different source. What this means is, as the data changes, either in the hypothetical, in my change set, or in the outside world, You get an immediate view of the change. Who wants one of those? Would you like it if your Terraform told you in advance that it was going to not break? Wouldn't that be dope? I want it. I wanted it so bad, I built it. Okay, so thank you so much. Keeb, good job. So, oh, wait, we kind of glossed over approvals. James has a question. Hit me.
Where does the code go? Remember you were showing us that JavaScript-ish stuff?
Yeah,
Does that go in there on the domains?
there's plenty of code. I'm going to get to it in a hot second. Yeah, there's lots of code. But again, the code goes into the model, right? So like you can interact with the model without writing code, which is great because I can decide what kind of interaction I desire. But one thing we did was approvals and multiplayer. So just like, let's bring it back in for a hot second, right? Those approval things are set in the model. So how many of you have a structure where you do control of who can make changes to the infrastructure based on who has access to a repository? All of you do. Again, ridiculous, right? Now that data lives on the model itself. You can say this model, if anybody touches it, I need to approve it, right? You can say, then you can use that across all the different interfaces you use. Yeah, super good. Okay, so what I'm going to do is apply this change. So you might notice here it's got two actions. So this is part of that operational transform. It knows that there isn't a real world resource attached to this VPC or this subnet. Yeah? And so if we want to create it, we know we have to go build them. So when I apply this change set here, I'm going to approve myself because I'm the boss. Okay, so now what we're going to do is go out and it's going to create those particular things. So while it's running, what's actually happening, ooh, why'd we die? Oh, I didn't parent him. Keeb saw it coming. He knew it was going to happen. He was like, you messed it up. Okay, so what we're going to do is set their parent real fast here to the region. You need it too. But notice that what I just did, I created a new branch, right? I just forked the universe. I said, oh, it should be different. I need credentials. So one thing that's cool is it remembers that I intended to take those actions. It knows that what I wanted to do was create those things and that something has gone wrong. So now I'm going to apply this change set, which looks good. So that's going to solve our problem. Yep, thank you so much. Just a little dancing here. Then when this change set applies, now we can come back, and I'm just going to retry the action again. So think about how many times something goes wrong because you had a minor misconfiguration, right? You're like, oh, everything was right-ish, but I forgot that one value I needed and the request failed. And then you had to go back and retry all of the crazy, right, that was inside of that repository. Now it's going to just work. It's going to take that. It knows it needs to create the VPC first. Then it's going to create the subnet, right, because the one has to come after the other. And those things just work, right, which is great. So one thing that happens here is we have a history of everything we just did. So we can go look. Here's the actual function that we ran at that time. And so what we're storing isn't just the function now. It's actually as it was run. So here's the exact arguments that were sent. Here's the exact code that it executed. Here's the exact result that it produced. Here's the logs the function actually spit out while we ran it, right? And we have this for every single function across the entire system, right? You can also look at it this way. So you can go see like, hey, here's every single low-level thing that's happened across this whole crazy hypergraph of functions. So if you think about this in terms of compliance, right, or in terms of those sorts of details you have to emit, you can start to build up from the primitives of this model really detailed information about who did what, where, why they did it, what the impact was, then what side effects it had, what other things it impacted, right? All that information trivially easy to compute. Okay, so the other thing that happened here was secrets. So when Keeb actually added this thing, he went over here and added this credential. And so credentials sounds complicated, right? I have to actually, I'm going to do encryption, there's all kinds of stuff. How, given your knowledge of the theory behind the system, do you model credentials? Come on. Someone knows. Secrets Manager, yes, you could use Secrets Manager. How would you, if you wanted to use Secrets Manager, how would you use the theory that I presented to you to integrate with Systems Manager? I would use a model. I would take plain text as input. I would take the thing you want to encrypt. Then I would encrypt it, and I would store the ciphertext. Yeah? And then later when I need it, what would I do? I would decrypt it. I would just take, and how would I do decryption? Secrets manager. I would use a function, yes, thank you very much. And what would the inputs to that function be? They would be the ciphertext, yeah? And then it would have 2 arguments to the function. It would need the ciphertext and the key. So I could then decrypt it, and then that's exactly what we do. This was not hard to implement. This is the core of what you do in Vault. How many people run Vault? Only now, it's super flexible, because now you can integrate with Secrets Manager. How would we do it? I would write a function that integrates with Secrets Manager. What's it do? It takes the input, sends it to Secrets Manager, stores a reference. When I need it later, goes and gets it. Ta-da! It all just kind of falls out of the theory. OK, what if I had other VPCs, right? What if I was like, hey, it's cool, you created one, but I want to know which VPCs I already have, because I want to use one of those. So I'm going to create another change set. We'll call it discovery. I'm going to go back to our VPC here, and I'm just going to run a function on it called a management function. And what these do is let you program the simulator. So instead of programming like the outside world, I'm just going to drive system initiative sort of from within system initiative. And in this case, we're going to do it to discover all the VPCs that exist on AWS. So I run this function. It's going to look at our account, right? It's got the region already attached. And now it's going to go just figure out what all the VPCs are that exist. And it's going to pop them out in this big graph, if I actually ran it. There they go. There's a bunch, turns out, because this is our demo account and we use them all the time, right? So here's every VPC that exists in AWS. That moment is the moral equivalent of discovering all those things, writing their definitions, creating the code, and now I can manage them, right? All the component side is filled in. If I apply this change set, it's going to go out to the real world, grab the actual resource data, and start updating it in real time, right? Super, super cool. How hard was this to do? Not hard. Because why? Just a function. And the output of the function is other stuff you want to create. And so you store that, then we run a thing that takes those things and then creates them, puts them on the graph, puts them where they belong, and ta-da, you've got the goods, right? Super good. How hard is this to do without a model? It's the same. You lie. You lie. The first thing you have to do if you want to do this is build a model. It's literally the first thing you would do. If you wanted to do discovery, you'd be like, but what's the data structure? How do I think about it? Where do I put it? How do they relate to each other, right? It's actually quite hard. What if I wanted to modularize this? What if I was like, hey, these I need lots and lots of one VPC and one subnet. So I can do this. I'll just highlight them. I'm going to say, go, create me a template. We're going to call this template like ConfigManagement basic VPC. Yeah, typos be damned. We don't even care. So what it's going to do is run a function that does what? Oh, creates code. So what it does is goes and writes the function itself that then will actually rebuild the thing we just had. So if we come over here and we look at its schema, this is the definition of that resource itself. So we'll come in here and we're just going to add, like, we're going to add child. How am I doing for time? I'm good. And then we'll do a new prop snippet. And this one's going to be like, we'll call it IP range, right? So we're just going to make it so we can feed the IP address into this thing first. And then we're going to click this regenerate button. OK, that's cool. But I know that you don't want to type code into the web browser. Yeah? You don't like that. You didn't like it, right? You were like, but I like my editor. So me too. So here's what we're going to do. I'm logged into this little homie. We're going to go to this config management directory. And we're just going to look at what we have inside of here. So one thing we have is this directory called change sets. What do we got? Ooh, there's my misspelled discovery. Let's pop into Vim. OK. Oh, don't fail me, network. Come on now. This is the moment the Wi-Fi crashes. OK, so now we can come look. Let's go look at the schema. All right, so we're going to go fetch, which one do we call it? We call it config, right? There it is. It's a little the network. All right, so now you have functions, definitions. So we'll go look at the function. In our particular, like when we actually want to see this thing, it's over in management. Probably should have run a find before I did this, so it was all cached. Ooh, it's locked. That's fun, because I need to unlock it. Which one did I get to? All right, so I'm going to back up here. So I'm going to create this directory. It's called unlocked. Now, I actually have a directory that has all this code. So by unlocking the function, now I can edit it in my editor. So in our case, we're going to come inside here. And this is the same code that you were seeing here, yeah? And so what's happening is we've basically built a fuse file system that knows how to talk to the underlying data structure, right? So this model that we have of all this information, one cool thing about having all that data as a model instead of its source code is that now I can put all sorts of different interfaces on top of it, right? So this one is a file system, which allows you to do all kinds of useful and clever things. And so then if we want to take this guy and set it up, I have like the variables here, the IP range. I've already deployed this. That's what happened. So yeah, we got a little mixed up in my demo. That's the bummer. You don't care, because I've run this before. It's the exact same code. But basically, see this here where it says like backtick vars IP range? That's just going to take that IP range and stick it into the template. So if we come back over here and we say, let's go run it. So I want a basic config management template. Basic. I just got to update it real quick. Ooh, I didn't actually put in the IP range. So now it's going to run, and they're just going to say undefined /16. What a bummer. But that's cool. We can just do it. 10, 0, 1, 0. And we'll just run that again. And you'll notice that these two are going to light up. And that's because what it's doing is changing their properties. How did that work? Yes, it was a function. It just reran the function. It just took it again. It knew that the inputs had changed, and then it automatically changed the outputs idempotently, right? This is the equivalent of what you do. How many people have tried to be a platform engineer? Have you renamed yourself a platform engineer yet? Or are we mostly a room that avoided it, right? So like, but this is basically modularizing things. This is what you do. So like using this model, you would just build the infrastructure you want to see one time. Then you could just turn it into a template. Then you could modularize it. Now you give people an interface that's that high-level semantic component you want to run, and then you drive it from there. OK, this is the same mechanism you would use in CI. So let's say you wanted to like create a bunch of VPCs for some random reason every time that you merge code to GitHub. So this is a GitHub action that knows how to do that. So it just calls a component inside System Initiative, sets a couple properties on it, and then calls a management function. So like, let's say you wanted to deploy your application, right? How'd you do it? You'd build a component that takes in the version you want to deploy. Then you have a management function that actually transforms the infrastructure data, schedules which actions to run, then runs them. Let's say you wanted to make sure that that only happened with proper approvals. They're all in the model anyway, so you have to do this much. Nothing new, right? Because they were already in there. You don't need to put them anywhere else. You don't have to do anything. They just happened, right? Sick. OK, last demo. Let's say you have information in something like vSphere. How many people have had to migrate a workload from vSphere? Yeah, a bunch of you have. OK, so we're going to do that now. We're going to migrate a workload from vSphere to AWS and just like show you one more time sort of the power of the model. So we'll come in here. We'll call this vSphere. Oh, sure. A view is just a way, like one of the things that happens in System Initiative is you have this like visual representation of all of these models. And when you have a lot of them, they get it's a lot. So if you have like thousands of things in a single perspective, it's kind of brutal. And so we give you this idea of a view that just lets you sort of put things out of the way, you know? So you can tuck them up, or you can hide them, or you can do what you want to do. In this case, we're just deciding that like my vSphere view is unique, right? So I will start.
But it's still connected to all the other.
Yes, everything that's there, everything that's inside the system is still there. You just can't see it, and you can still link to it. So like, for example, earlier, these things are all linked to the region and credential that he created here, right? They're just in separate views, right? This is how you can think about having like a network layer, that's being managed by a network team. This also ties into things like authorization. So the way you would do complex authorization is you would just put things into views, and then you decide who are the people that are required to approve changes whenever a component within that view is impacted in a change. And then we can compute the list of all the people based on the change you're proposing that need to review it, right? Sick. Okay, so here we're going to build we're going to take a credential. Luckily, I already have one, so we're just going to call it DC. We'll call it vSim. I don't actually have vSphere here. I just am using a simulator that helpfully they built. I already had a credential ready, so I'm just connecting myself up to vSphere, and then I've got a data center that I need. So I'm going to come over here. I'm going to add a data center. This one's called DC0. Luckily, I already know what it's called, so I can come into this management functions list, and I can feed it the resource ID because I know what it is. And then I'm going to just run import.
Is it similar to like Terraform import? So it just provides with the URL or whatever unique identifier?
Yeah, I just told it what the unique identifier was, and now it went out and grabbed it. It turns out the only attribute of those things happens to be that it's DC0. But yes, it basically just imported that thing from the outside world. But now we're going to go write another management function. That thing's job is to actually just go find the VMs. So we'll say discover VMs. And now what it's going to do is die. Oh, because it's not a frame. Yeah, one more step. Sorry about that. There it goes. Now it's going to go find them. So now it's got 4 VMs, right? Turns out they're kind of tiny, but now what we're going to do is take a management function called VMware vSphere to AWS EC2 in the lift and shift category. Okay, so we're going to take this guy, we're going to connect our VMs up to it, so we're just going to say, hey, this one, this one, this one, and that one. And now we're going to take those, and we're going to migrate the compute workloads to AWS. Management connection. Oh, again, I'm forgetting steps in my own demo. So I need to also connect this to a credential and a region. So we'll just do that now. So this now knows where it's going to migrate the workload. Because I hadn't done it, it didn't know where to migrate the workload, so the function failed. So here I'm going to come in. I'm just going to say, now I can migrate the compute workload, and it's going to work just fine. Boop. No. Oh, because I can't parent it. This is what I get. Live demos. James did me wrong. I'm kidding. James is a delight. There you go. So now you got 4 EC2 nodes, right? And those EC2 nodes match the exact same things that happened inside the VM, right? That management function, roughly 50 lines of source code. Yeah? Because we've turned what is a really difficult automation problem into a pretty trivial data transformation problem because the models themselves are complete, right? So if you imagine, right now, we have complete coverage of all the AWS APIs, but soon there'll be coverage of the Azure APIs, coverage of Google, coverage of vSphere, right? And now all this information that you need to do your work just works. Think about the side effects of that. For example, let's say you want to do cost analysis. You want to be able to produce a number that says, how much would it cost if I made this change to the infrastructure? How would you do it? You'd write a function. What would it do? It would compute the cost. Then what would you do? You would build a UI that allows people to look at cost on different dimensions. How hard would it be to do? Say it with easy. It'd be easy. It's so easy because it's just a function, and you know how to write it, and you already have all the data. You don't have it right now. It's all spread out. Makes you want to die. How many people have had to do compliance? You had to do compliance security scans? You know what's hard about doing that? Getting the data. It's so hard. Guess what you have now? What do you have? Say it to me. Oh, you have the data. Oh my God, fuck. You have the data. It would just work, my friends. I am Adam Jacob. This is infrastructure as model. That is a hypergraph of functions, and this shit is your future. You can come talk to me about it on Wednesday. Today or tomorrow, this is how it's going to be because it's so much better. Let's fucking go. There's a workshop on Wednesday. We got a little booth. You can come talk to us. We'll tell you more about it. Thank you.